In this example, we're going to use random number generators to make synthetic data or a simulation for this real-world example. So in this scenario, we're trying to make 12 inch by 12 inch or 1 foot by 1 foot square tiles out of granite. But the devices we're using to cut them, or the saws we're using, can't make them always exactly 12 inches. So we see that the saw that makes the horizontal cut makes it on average 12 inches, but it makes it with a normal distribution with a standard deviation of 0.2 inches. So sometimes a little bit more than 12 inches, sometimes a little bit less. And then the cutter that makes the vertical cuts on it is also on average cutting it 12 inches long, but sometimes a little more, sometimes a little less, and that has a standard deviation of 0.15 inches. And we're going to assume that the two cutters are independent of each other, so if one of them cuts it too large, the other one, it doesn't affect if the other one cuts it larger or smaller. They're going to be independent type of events. All right, so I guess the first question before we look further is, where would these numbers come from in real life? Well, in real life, what we would do is we would probably take a sample of, say, 1,000 of the tiles, and then we would go and with a ruler or some other device measure how long is the horizontal length, how long is the vertical length. So this would be the first part of what we did in this week's lesson, where we have just a data set, and we can look at the mean, we can look at the standard deviation. So we have 1,000 data points that we collected from the tile manufacturer, and we can take the mean of that data, and it turns out to be 12 inches. And for the horizontal cuts, we find that the standard deviation is 0.2 inches, and for the vertical cuts, we can find the standard deviation of those 1,000 data points to be 0.15. And then we would take that data, we could put into some normality test like the Lilliefors test, and it would say, yes, we can treat this as a normal distribution, and then that's where we kind of begin this problem. So we're working under the assumption that these lengths are normally distributed in order to do the rest of the problem. So we'll address the first part of the question. So part one, what can we expect the distribution of the area of the tiles to be? Again, nominally, if it cut them perfectly 12 by 12, then they should all be 144 square inches. But because sometimes the horizontal cut's a little big or a little bit small, and then independently of that, the vertical cut is sometimes a little big, a little bit small, we're going to see that the actual area of each tile could be a little bit more than 144 or a little bit less than 144. But we can't necessarily predict without using math from statistics that we don't have yet, and for more complicated problems, really the math doesn't help us too much. But we can, by simulation, come up with these results. So what we can do in simulation is synthetically create as many tiles as we want without actually having to manufacture them. So what I can do is I'm going to start with, I'll call H. Let me clear out everything first. H is going to represent the horizontal lengths of all of my tiles. Now again, they tell us that the horizontal lengths are on average 12 inches and have a standard deviation of 0.2 inches. And it comes from a normal distribution. So I'll start kind of small here. So what I can do here is I can generate this vector H, and what does this represent? This represents if I had 1,000 tiles, this is what I could expect the horizontal lengths of those tiles to be. So again, we see that some of them are a little bit bigger than 12, some of them are a little bit less than 12. And just so we can observe it for right now, if I made a histogram of this, this is going to look similar to the actual data that we collected. So again, on average it's around 12, but we see that with some frequency we have larger tiles, and with some frequency we have smaller tiles. And it's normally distributed around that mean of 12 square inches. Alright, so that represents if I made, in this case, 1,000 tiles, and I'll actually make that a variable that I'll call samps, because that way I can change it a little bit as we go. Oops, I forgot to make samps actually 1,000. Okay, so I have 1,000 tiles at the moment. Each one I have, for each of my 1,000 tiles, I have the horizontal distance for each. Now independently, each tile also has that vertical length, which has that same mean of 12, but it has a standard deviation of 0.15. So again, looking at the values that v takes for that vertical height for each of our 1,000 tiles. Some of them a little bit more than 12, some of them a little bit less than 12. And just so we can observe what that looks like if we look at the histogram. Again, centered around 12, and we can keep running that with different sets of random data. That's what we get. And let me use more samples just so we can see how this works. So I'll just start with, actually no, I'll stick with 1,000 for now because we'll see what changes here. All right, so we have our horizontal lengths of each tile and the vertical lengths of each tile. Now, if every h value represents the horizontal length of a tile and every v represents the vertical length of the tile, let me group these together a little bit so we can just see them side by side here. So if I go just to the top of my data set, what this is representing is for this first row, that is if I made a tile, that would be for tile number 1 what its horizontal length was and what its vertical length was. Row number 2, that would be the horizontal length and the vertical length of the second tile. Again, these measurements are independent, which is crucial to be able to do this. Otherwise, we need a little bit more advanced techniques to be able to do that sort of analysis. But again, so this is tile 1, 2, 3, 4, 5, all of them synthetically created. So I have 1,000 right now synthetic tiles. So what I'm interested in is for each of these tiles that I made, since for part 1 I'm interested in what I can expect the average area and what the standard deviation of that area to be, I want for every tile, I want to be able to figure out what is the tile's area. So since they're rectangular tiles, they should be square, but they're each a little bit rectangular here. To find the area of a tile, I just have to know that tile's height or h value, and I have to multiply it by its v value, because that will be side length times side length, or height times base. Right, so looking here, again, I have 1,000 values in A, and this represents the area of those 1,000 tiles, with the h's as specified, randomly generated, and v as specified, but randomly generated. So this is A is 1,000 values, and if I look at a histogram of A, get a little bit better look here. All right, so we see for our area here that the mean looks to be about 144. I'll get a more exact answer in a little bit. And we see that it looks roughly also bell-shaped or normally distributed. But we're going to want to run a test on that. So what we want to do is answer the first question. What can we expect the distribution to look like? So I can take A and I can find its mean value. And we see that the mean of A is pretty close to 144. So 143.9948, I'm going to call that a mean value of 144 square inches. And again, if all the tiles were perfectly square, every tile should have 144 square inches. But we see that because of that randomness, because of that distribution, that some of them have a little bit more area, some of them a little bit less area. So what I can look at is what's the standard deviation. Let me actually print that out here. And we see that the standard deviation, when I'm using 1,000 samples or 1,000 randomly generated tiles, that I have a standard deviation of 3.06. So the tiles have a mean of 144 square inches, but a standard deviation of 3.06 square inches. So this is what I would call the tolerance, or I could express the tolerance as a standard deviation. In this case, if this is how our tiles are cut with this sort of distribution, then we can expect that if we were to measure the areas of all of our tiles, that it would be 144 square inches plus or minus 3.06 square inches, where that's the standard deviation. But let me make a little bit better histogram here of my data. I want to use, usually a relative frequency histogram is going to be better to use. So the first thing is I want to properly bin it. Or at least bin it better than 10, which is usually not a great choice. But sometimes it is. But I'm going to use Sturges's rule for this again, because that is usually better for normally distributed data, which this at least appears to be. So it's the length of A plus 1 and the ceiling of that. I forgot parentheses there. And now I can run this line, and it suggests having 11 bins instead. And I want a relative frequency histogram, so I do want to not use the default settings here, and then I can use a bar, and it will be C versus X over sum of X, just like we did in previous parts here. Right, so we see by dividing X by the sum of X, which in this case is going to be 1,000, or the number of samples really. Now I have my relative frequency histogram. Okay, I'll make that black, and I want my X label. This is area, and this is going to be measured in square feet. And then Y label, this represents my relative frequency. And I'll put a grid on and tighten the axes. All right, so now I have a pretty nice histogram that represents what I would expect the distribution of the area measurements to look like. Again, this is only for 1,000 tiles right now. We're going to come back to this in a little bit once we do part 2 and refine this out a bit. But this is what we expect that distribution to look like. Let's see what happens when I kind of keep rerunning this a little bit. Well, n is always 11, but I'm interested in that mean and standard deviation. We see that the standard deviation changes a little bit. We have 2.9, and our mean is 143. And when we rerun this, we see it's close, but it is changing a little bit. So our estimate is not necessarily consistent. And let's just see what happens. What if I use fewer samples? I arbitrarily right now chose to use 1,000 samples. What if I only use 100 samples? Well, we see the standard deviation is much different. It's only 2.67. The mean is about the same. But it keeps changing. And what if I only used 10 samples? We see that this it keeps wildly changing here. From run to run, where I only am using 10 samples. So how do we know how many samples is enough? As we looked at in the previous slide on simulation, in general, the more samples you use, the better. But the more samples you use, the longer it takes to run. And we also want to kind of be sure that we're using enough of these samples. If I go up to 1,000,000 samples, then we see that our plot looks a lot nicer when we have 1,000,000. We see the mean is pretty close to 144, and now our standard deviation is at 3. And if I run it again, I get pretty much the same results time after time. So that's one thing we want to look for is if we keep rerunning the simulation, are we getting similar results? But what we can look at here to test, have we used enough data points, is we can look at convergence. And that's what we'll test in part 2. We want to see how many samples does it take until we have, again, what's called convergence. And there's a lot of different ways we can test for convergence. I'm going to base it on the mean of A. And we'll see how this works in a minute. So I'm going to go up here. I'm going to actually run this for, I'm going to make this another subset here. I'm going to use actually 10 million samples, at least to start, so that we can see how this is working. And this part is a little bit tricky for what I'm going to do with this. What I want to do is, I ran it 10 million times, but I'm going to act as though I'm only using 10 samples and then 100 samples, etc. In this creation. So bear with me for a moment until you see what's happening. What I'm going to do for this test is I'm going to subsample the values I have in A. So basically what I'm going to do is I'm going to start with only taking 10 tiles, seeing what the average area is. Then I'm going to look at 11 tiles, then 12 tiles, and I'm going to keep taking the mean value as I add more and more tiles. And we'll see graphically what's going to happen. Right, so that's what n is going to represent, is how many tiles I'm going to be using in my subset. And then what I'm going to do here is I am going to kind of keep track of that in, I'm going to call it a variable m. And I want to pre-allocate this because this will take a while. So for every n, I want to store what's the mean if I take, again, the first 10, then the first 11, then the first 12, until I'm using all the tiles that I have. Right, so this is where it starts to get a little bit trickier here. So in every value of m, I'm going to take the mean from a, from the first value of a until the kth value of n. And I'll again reiterate what I'm doing here. So when k is equal to 1, I'm using n of 1, and if we go back up to line 122, that's 10. So what I'm doing on the first iteration of this for loop is I want the mean value from tiles only 1 through 10. So let me just arbitrarily set k to 1 for this test at the moment. So again, I'll kind of work from the inside out. If I just take this a value here, that is the first 10 areas of tile, or from the first 10 tiles, those are their 10 areas. And I just want the mean of those values to start with. Right, so the mean of the first 10 is 144, and I save that to m of k. I go and I increase the value of k, so k would be equal to 2. And now what's happening, I'm taking the mean of the first tile through the 11th tile, since that's n of 2, which is going to be 11. So what I'm doing is I'm taking more and more tiles, I'm taking their mean, and I'm storing it into this m of k. So let me run this, and we'll see what the data looks like, and then I'll explain a little bit further. Alright, so that takes a little bit of time to run, but now we can look at our results. So for convergence, we're just going to look at graphically that you can come up with rules similar to the homework problem with temperature converging in our plate. We want to see how many terms is going to be appropriate to make some of these estimates. So I'll start with just plotting so we can see what it looks like. So this is the number of terms we have, or the number of samples we have, versus what that average is. And we see here that it actually isn't that helpful to have a plot. Usually for these, it's good to have a semilog plot in X. So the number of samples I'm using, I want to be a log scale, and then the average value is going to be in a linear scale on Y. Right, and we see it starts to look a little bit better. I'll put a grid on so we can see what it looks like. And let's make it a black line here to see what's happening. Right, so again, X is the number of samples, or the number of tiles that we're using. And in this particular test, I'm looking at what the mean value of the area is. All right, so let's see what's happening here. So when we're using fewer samples, so 10 to 100, we see that as we keep adding more samples, that average area is fairly drastically changing as we keep adding more and more samples and take the mean of more and more samples. But we see what eventually starts to happen here is that the change in the mean area gets smaller and smaller and smaller, and it's changing less and less as we add more samples, until eventually, once we get to around, I would say 10 to the 4th, it's relatively flat in here. So as we add more samples, the mean area is not really changing, and we get to this average value of 144. So how do we interpret this? If we use too few samples, so let's say we did only use 100 samples, let's use even fewer to start. If we only used about 15 samples or so, or 15 samples, we would have concluded that the average area was 144.8 of our tiles. But we see that that's an overestimate because we didn't use enough samples. And then if we start to use more, we would actually start underestimating. So what we're looking for here is that the percent change is getting smaller and smaller and smaller the more samples we add. So graphically, once we get to around 10 to the 4th, it's pretty well flat. So again, what I would indicate, or what this graph suggests to me, is that we should use at least 10 to the fourth samples, since that's where the plot really starts to flatten out here. And we can use more than 10 to the fourth. The downside of using more than 10 to the fourth is we will get increased precision, but we have decreased time. But we don't want to just necessarily arbitrarily say let's use 1,000,000, because without this convergence plot, it's possible that even at 1,000,000, we still have kind of big changes as we're adding more and more. When we see this flat line, that indicates that if we have at least that many data points, that we have a converged solution, and then the estimate we're getting should be pretty good. All right, so this actually answers, or our inference from this answers part 2. We have enough samples as long as we have, I'm going to say roughly 10 to the fourth. Let me actually go back up to part 1 and refine this a little bit. So I'm going to use, in this part here, 10 to the fifth samples when I'm doing this. All right, so I'm going to recompute all of this for 10 to the fifth, or 100,000 samples, and then answer part 1 again. Now I know that my answer should have converged. So rerun just section 1. So this is the nice histogram that I get when I use 100,000 samples, nice and normal looking. And then we see now we have a mean of, I'm going to call it 144, and with this many samples, our standard deviation is also pretty reliable, 3 square inches. All right, so this answers part 1 and 2. Now using this same information that we have, I want to answer part 3. So whoever is buying the tiles from us, when they install them, they can have at most a standard, this is not in standard deviation here, they can have a length of a side of at most 12.25 and at the minimum 11.75 on either the horizontal length or the vertical length. So again, part 3, this is not talking about a standard deviation, this is the physical measurement of the tile. So yeah, if it's too much bigger or too much smaller, they won't be able to install it in the floor, and that's the goal. So if this is our manufacturing process, and this is what our buyer wants, what we're trying to see is what percentage of all the tiles we manufacture are going to be acceptable for us to sell. Because if they're too big on the side or too small on the side, then we have to destroy them, or we can't sell them for full price. So we can go back to this synthetic data that we made. Remember, we have all these H values, we have all these V values. Now again, the H values are the horizontal length. So what we want to test here is for a tile to be acceptable, its H value cannot be greater than 12.25, it can't be less than 11.75, and its V value has to have the same rule. So what I'm going to look at here is I want to see where are all the tiles where the H is less than 12.25, Right, so that is of the 100,000 tiles, those are those that have a H less than 12.25 inches. However, it also simultaneously has to be larger than 11.75. So what this is doing is it's looking at all of my tile values, and both of these things have to be true simultaneously. So again, if I look at the list it's making, it's 1 if both of these things are true, and it's 0 if one of them is false. So if it's either bigger than the 12.25 or smaller than 11.75, it's returning that 0. For the tile to be acceptable, the H has to be between those two values, but also it has to be true that V is between those two values. So I can add more of these logical tests here. So the V value for each of them has to be between those two values. Right, so again, running through these, it's 1 if all 4 of these conditions are true for any one tile, and it's 0 if one of these is false. And I'm going to call this good, and rerun this. Right, so we have here, when I rerun part 3, I have good is a collection of zeros and ones, so it is 100,000, it calls them logicals, or booleans, or zeros or ones. So for this test with 100,000 tiles, what I want to see is what percentage of them are acceptable, because that's the percentage that we'll be able to sell, and everything else we won't be able to sell. So what I can do to see what percentage of them is good, well, again, looking down here, it's a 1 if it's good, it's a 0 if it's not good. So what I can see is of this 100,000, if I add up how many of them are 1s, it tells me that 71,255 of them satisfy that the h is within those bounds and the v is within those bounds. And if I divide that by how many, I guess I can use h here. Remember, originally I manufactured 100,000 tiles, but according to my simulation, only 71,255 of them were within spec, within the requirements of the h and the v value. So as a percentage, if I take how many of them are good versus how many I had to manufacture and multiply by 100, I find that under this manufacturing process, only 71.3% of the tiles I make are acceptable. So if I want to make money, that's probably not enough. If I have to throw away nearly 30% of the tiles I make, then I'm losing a lot of money in the manufacturing process. So as far as the analysis goes, this is where it would stop. Now, where is this useful? Well, if I know that this is what my buyers want, is it's within plus or minus 0.25 of 12 inches, and this is my manufacturing process, I'm seeing I have to throw away 30% of the tiles, this would tell me as the manufacturer that what I would want to do is look at my manufacturing process and tighten up those tolerances. So let's just go a little bit further than what the question asks. This does answer part 3, but let's redo this a little bit. So I'm going to go back. Let's say that I improve my equipment and it's able to make cuts with a smaller standard deviation. So let's say I can reduce my horizontal cut instead of 0.2 inches as my standard deviation, I can halve that to 0.1. And for my vertical, let's say I buy a new saw and it does a better job, and that's also at 0.1 here. So let me rerun. I make a new set of 100,000 points, and I have new h and v values. So again, what happened? The mean is the same, but the tolerance is tighter. It's a better saw, so the standard deviation goes down. With these new numbers, let me go down to part 3 and now test this again. Clear this. All right, so I reevaluate good, and we see now, with these tighter tolerances, with these better saws, 97.5% of the tiles I manufacture are now within these limits. So now I only have to throw away 2.5% versus the 30% with the original equipment. All right, so let me recap this since we did a lot in this problem. Let me go back to these original values. So the first thing I did is based on the data that was provided, I made in this case, 100,000 tiles, synthetically making them on the computer or in simulation. So based on the data, I came up with every tile's horizontal length and every tile's vertical length, drawing from this random distribution from a normal distribution. Then for every tile, I can compute its area because I know each tile's height, or h value, and each tile's vertical length. So I got the value of their area. So I saw for 100,000 tiles that the distribution of the areas turned out to be, I'll rerun this again, 144 square inches, and I had a standard deviation of 3 inches. And this area is 9 feet actually, it's in inches squared, so I'll correct that. All right, then in part 2, what I did is I wanted to test, did I have enough samples that the estimate I'm making was good? So I looked at that convergence plot and I saw how many samples did it take before, in this case, I was looking at the mean value of A, before the mean value of A started to flatten, and then adding more samples did not really change the mean value of A anymore. And we saw that graphically, it took about 1 times 10 to the 4th, or 10,000 samples for that to happen. So I decided to use at least 10,000 samples, so that's where I chose then to reevaluate part 1, the 100,000. Then in part 3, under the initial way that these are cut with these standard deviations, I wanted to see how many of the tiles were acceptable. So how many of the tiles fell within H value of 11.75 and 12.25, and simultaneously had a V value between 11.75 and 12.25. So good is where all of these things are simultaneously true. So again, I'll show good is 1s and 0s. 1 means that all 4 of those are true, and it gave me a 0 if at least one of them was false. So only where it's 1 are those tiles that were acceptable. So the last thing I did was I saw how many of them were good as a percentage versus how many I manufactured. I made in this simulation 100,000. It turned out that about 71,000 of them were good. So we saw that as a percentage, 71.1% of the tiles I make were acceptable under these original conditions.